Labguy here. Today we're going to resume the PhiloCam project. This is PhiloCam Part 6. The PhiloCam project up to this point has been getting its scan drives from two audio signal generators. This approach has reached its practical limits. I am now going to design my own scanning format for the PhiloCam. It's based on the Model 61 Robot Research viewfinder monitor for the slow scan television system I showed in the last video. My system will scan a 267 line picture, 15 frames per second progressive scan. So to begin this process, we're going to need a sync generator that produces pulse trains at those rates. Then following the sync generator will be the design and construction of the analog deflection boards, which should be pretty straightforward this time, based on the experience I gained from the project called the Chief, my test pattern generator. And then we will begin to integrate in the image dissector tube into the video chain and optimize its circuits for this video frame rate. So this will probably occur over several months of work. So to begin with today, I will give a description of the sync generator and how it's going to work. And then you can tune out, or you can watch me assemble the new sync generator board, because I have a horse and cart problem. The new sync generator is based on clocking timing patterns out of flash memory chips. So I have two avenues to work down. One is to build the hardware, and the second is to write software that will produce the bit patterns for the memory chips. So today we're going to look at the hardware that is used in this system. So let's go look at the schematics now and see how that's going to work. Here's the schematic of the new sync generator on my computer screen. At the end of the video I will include a frame insert so you can see it in high resolution and examine it for yourself. This is a very straightforward system in that it starts with a master clock oscillator of 4 megahertz. The 4 megahertz oscillator drives a simple binary counter stream with 19 address bits. That can count to 524,287. We need 166,667 as our divide frequency, which will be decoded by two memory chips. Actually, one memory chip will do the actual decoding. The primary memory chip is the sync pulse flash memory. I'm using flash memory so that as I develop the bit patterns, I can reprogram the chips without throwing away chips. These are half megabyte flash memories that have a speed of, I believe, 100 nanoseconds, I think. They're very fast. I'm running them at 250 nanoseconds, so well below their top speed. They're permanently enabled so that as the counters run, the data is simply clocked out of them and latched. Because when the address bus changes, there's even though this is a synchronous address bus, all the bits should change together. The outputs can get glitchy, and I don't need glitch pulses in my sync streams, so I relatch the output of each ROM with an 8-bit latch. So this chip will contain the most important pulse it contains is the top count pulse, the state machine reset. This is called a state machine. And you can think of it as one of those little music machines you find in a jewelry box with the little drum with pins on it as it goes around plinking the little musical keys. This is exactly the same thing. This is the spring that turns the motor. This is the motor that is telling us where we are on that drum at any moment. And this memory contains ones and zeros. If there's a 1, there's no pin, and if it's a 0, there's a pin at that location. Think of it like that. And so this is streaming out a stream of 8 separate streams of 1 and 0. So the most important pulse is what's called the top count or the state machine reset, which will occur at count 266,667. And that will come around and reset the counters back to 0. So that will give us our repetitive frame rate. If you take 4 megahertz and divide it by 266,667, you get 14.99998 hertz. That is the frame rate. That's 15 hertz no matter how you slice it. And at every 999 counts of the counter, the output will output a horizontal sync pulse. So the sync signals that are coming out, there's 4 of them. There will be vertical drive for the scan circuit, horizontal drive for its scan circuit, composite blanking for blanking the video amplifier, and composite sync to add to the video stream to produce a composite video signal. In addition to generating sync, and to help in debugging this system before we go on to the scan generating board, there's a second memory which will contain 4 test images. I don't show any circuitry right now to select which test image will be displayed, but that will be added. And it will output non-composite raw video. It will contain only grayscale information formatted within to come out as a video stream. And so I can put 4 test patterns in there. For instance, a square grid that I can use to align the size of the monitor, a nice circle for the same reason to check linearity, the Indian head test pattern, things like that. So, you know, a picture of Labguy would be kind of cool. And I'm really thinking that it should contain a test pattern that says PhiloCam. So this video output, the output of that memory goes to a D to A converter where it will be converted to analog video, and that video will go to a switch which selects either the video generator or the video coming from the dissector tube, which comes much later. So that is the overall architecture of the sync generator as it stands right now. So for now, all we need to do is construct this hardware, because without this hardware, generating the bit patterns is just an exercise in abstraction. So let's move on to the assembly of this sync generator. What we're looking at here is the first experimental sync generator I started building for PhiloCam. It's got the crystal oscillator, and it has several 74HC163 4-bit up-down counters, which I was using as modulo N dividers to divide down the crystal to the various frequencies, 4 kilohertz for the line frequency and 15 hertz for the frame frequency. And it was working well enough, but with this density of logic, the complete sync generator would have outgrown this board. This board wasn't going to be big enough with this approach. So I've changed tack, and I'm going to use very, very large flash memory chips as poor man's state machines. This video is essentially going to be a real-time run as I wire this board, and you'll be able to watch me do that in real time. I'm going to start with the clock oscillator, which is a 14-pin device. I buy all my parts at Anchor Electronics in Santa Clara, near the corner of Walsh and something else. Alright, one 14-pin socket, 3 16-pin sockets, alright, we'll do a slight dress rehearsal here of lining these up. Come on. Gotta put on my eyeballs because old Labguy just doesn't see as good as he used to. There we go. These memory chips will come out into an 8-bit latch, and those are 20-pin. So let's go ahead and get out a couple of 20-pin sockets while we're at it and see if we can get everything into one row. That would be very interesting to see. And I like this arrangement. Now, of course, when I go to turn this over, these chips, these sockets will fall right out. So I'm going to remove the two thick ones. These two are taller from the surface of the board. So I'm going to take them out temporarily. And I have a nice, long, handy piece of Scotch tape. And we'll put that there and there, tag these down, and hopefully we can flip the board over and not lose them. And now you have no idea where they are. Let's see if we can zoom in a little for you. You still have no idea where those chips are. So the first thing I'm going to do before we get started is to tack the corners of them down. So at this point, we grab our magic pen and I do this on every project. You would be surprised how many errors are avoided by outlining the chips like this. There you go. 14, 16, 16, 16, 20, and 20. Now, the thing is, I don't know if you can see it, but the chip sockets are not level with the board. They're only held in by one pin at the moment. So now I have to seat them so they're flat. And don't put your finger over the pin that you're putting the heat on, because it will leave a neat little burned circle on your finger. And you'll make all kinds of embarrassing screaming noises, which makes everyone watching the video laugh uproariously. And I do like to be entertaining, but I have my limits. We tack the opposite corners. So that the parts will now stay put. Alright, we come back to these guys. And the question is, do they look better near the top of these sockets, or do they look better more centered on these sockets. They're not centered, are they? Poop. Watch your language, lab guy. There we go. I think that looks sexier. That's pretty good arrangement. Back to our magic tape. This time we can use the shorter one. Just so they don't fall out. Flip them over and we'll nothing like soldering all the pins on your socket, and when you flip your board over, the socket sitting cockeyed. There's nothing worse than being cockeyed. I should know. All right, sexy. So, oscillator, 3 address counters, a sync memory chip, sync memory latch, test pattern memory chip, test pattern latch. The next thing to do is to outline the 2 memory chip sockets. How does that look to you guys? Is it visible? It's visible. I've marked out where the sockets are, and you can see that. And the next thing will be to go ahead and solder up all of the pins so that when I'm putting the wires on, I don't have to do that. Now we're about to use up solder like it's going out of style. There, they're soldered. So, the next phase on these chips is to connect the power ground pins. The power ground. I did not misstate that. The power ground pins are typically the bottom left corner when you have pin 1 in the upper left. So, that's ground, 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 ground. The grounds, of course, on the 2 memory sockets are arbitrarily located. We'll deal with those separately. So, what I do on these, and I don't know if you'll be able to see it, is that underneath the edge of these, the pin is visible. You can get your soldering iron in there. This board has ground plane on the top. This does 2 things. One, it gives us convenient access to ground everywhere, and it forms a Faraday shield for the back. It also forms the ground plane for the signal routing. Signal, if you keep your wires flat to this surface, you get good transmission line characteristics. You get less ringing, you get good pulse transfers, and if you'll note by my construction technique, my wire running distances are reasonably short. The longest one is going to be here, from this farthest counter to this chip. That's what? 3 inches? Less than 3 inches. Very short lines. So the first thing we're going to do now is to go under these edges of these dip sockets and solder the ground pins directly right there. I wish I could show it to you. Directly to the ground plane. So The way I do that is I prop the board up like this so that I can get the soldering iron in there. And no doubt I'm going to stick my head in the picture where you can't see it. Can't see what I'm doing, but we'll try. So what I do is I get in there like this, and I heat the pin. There. Can you see it? Yes. Now we go to the next one. Your chips will thank you. This ground is as solid of a ground as you can possibly make. Okay, get in there and solder. There we go. This one will be easy to get to. He's kind of up in the air. There we go. A little more. All right. And ground. Now later, when we're wiring configuration pins that we have to pull up or pull down, that ground pin is a convenient place now on the other side of the board to pick up ground. So those are now, these chips and these two dips here are now grounded. There is the pin pattern. I'll insert a still picture of that when we're working on this. But as you can see, the pinning can be very goofy. And the ground power pin on those is pin 16. Is this one right here. And we need to ground that. That requires rework wire. I have this stuff in multiple colors. I like black for ground, red for plus 5 volts, yellow is for signals. I use orange for plus 12 volts, green for minus 5 volts, and other colors for other voltages. But we're only working with 5 volts on this board. What we're going to do is we're going to go through the hole to the top side of the board and pick it up here. We're going to pick it up on this side where the wire comes through and tack solder it down. I cut this notch in my reel to catch the wire. And I just pull it in there and it holds it. Now I have a length of wire to work with. We are zoomed in kind of close. So you see now I have the wire length that I need, and I strip off about an inch or two. So back to this side. What I like to do is just lay that flat to the table and stick the wire through the hole so that it protrudes down, hits the table. That means about 1/4 of an inch of wire is sticking through to the other side. We tack solder him down lightly. Don't over solder that side of the hole. And I bend him over, press him flat, pull him in there nice and tight. Just make sure he's wet soldered to the pin, and then cut off the extra. Put that there. Now, when I flip it over, you see the wire right here. So we reach over and we grab him, and we just bend him down flat to the board. Just like that. Come in and solder him down. Cut off the excess. Come back on this side now. I'm going to do it again on the other chip, but this time I won't talk about it. I'll just do it. Alright, all of the chips are now grounded. The next phase is to prepare their power pins with bypass capacitors. For those, I use, I don't know if you can read it, I use 0.1 microfarad 0603 size surface mount capacitors for this. 2, 3, 4, 5, 6, 7, 8. So I need 8 capacitors. I usually dump out more than I need. Now, those on the dip chips that I use, all of these dips in this instance, the highest pin number, which is on the upper right, that is the VCC 5-volt input. So we put a capacitor on each one of those, and then we will ground the opposite end of the capacitor in the same manner as we've just done those 2 sockets. So first let's do the 6 dip chips, starting right over here. I just put the capacitors on, only soldering the one end. So they go like this. They want to stand up on end, which is called tombstoning. Alright, so those are now soldered in place. Now we go back and we hit the ground end of each one with the solder. So we're going to solder them to the there we go. I'm going to start up here, and basically we go to the ground end of them and solder them to that pad. Don't worry about filling the pad with solder. That will not be an issue. But you do need to solder both ends down or the thing will get away from you. And sometimes when it's not quite soldered right, you can touch it up. There we go. Make sure that bridge is over. There we go. The 0603 size components, passive components, capacitors and resistors, fit between these 1/10 inch grid pads perfectly. So, now, those are soldered down. So now we come back with our wire again and just kind of curve it over. You reheat the pad and shove it through the hole so that, I don't know, 1/4 of an inch sticks out the other side. Bend it flat, cut it off. Do the next one. Then we take our tweezers and we grab our wires and we bend them over. Yeah, there's more wire than we need, but who cares, right? Bend them over. Can you see that? Then we come back and we solder them to the ground plane just like that. I kind of like to have a fat ball of solder across there. Alright. And cut off the excess. I may have just cut that one off. I did. Well, there's a will. There's a dead guy. Okay, that's soldered. That's connected. Okay, so all of the dip parts are grounded, power is grounded, and VCC pins are bypassed. Now we got to do these two guys. Their VCC pin is pin 32. Looking at our diagram, pin 32 is, pin 32 is up here on the top, not far from pin 1. So conveniently it's on an outside edge. So let me turn that around where I can see it. Turn this around right side up so I get it right, and we'll have a look. Pin 32, where the ground pin was the second pin over on the bottom row from the right, pin 32 is the second pin over from the left on the top. Right there. And conveniently, this is going to be very easy. Alright. Tweezers, please. Oh, I'm around the wrong way. Make sure you guys can see that. Grab the capacitor. 32. From this perspective is second pin up. He's on. One more capacitor. And he's on. If you let go before the solder cools, the part will stand up. That's called tombstoning, like a tombstone. It'll stand right up. So we tack the other end to the feed-through hole. And just like before, we'll put our wire through there. Just to be safe, we'll grab the ohm meter here and make sure those capacitors are all grounded. I can conveniently pick up ground on this. Ground, ground, ground. Yes, I know these guys are good, but since I know it's a fact, better check it, because as I've learned over the years, the quickest way to be wrong is to believe that you are right. Shortest path to wrong there is to believe you are right. Alright. Power and ground is now connected on all of these devices. I should say all these device sockets. It's break time for Labguy.